Greetings to everyone. My name is Puneeth Jubahanaya. I am a PhD student at SITCOM Research Group SNT at University of Luxembourg. Today, I will be presenting the demand-based scheduling for pre-coded multi-beam high-throughput satellite systems. To begin with, I would like to provide the outline of today's presentation. First, we're going to start with the introduction and then talk about the system model. And then we will define the problem statement, followed by the proposed solution. And then we will conclude with the simulation and some results. And finally, we will sum up with a summary. First, the introduction. The trend of user demand shifting from broadcast services to broadband services has made satellite industries investigate high-throughput satellite systems moving from single-beam to multi-beam coverage pattern. The figure on the left has a single-beam pattern, whereas the figure on the right has multiple beams which are much smaller in size and provides better throughput. However, the problem with the multi-beam pattern is the co-channel interference. So, it is very important to mitigate the interference. Precoding for multi-beam high-throughput satellite systems has been proposed as an effective co-channel interference mitigation technique able to boost the spectral efficiency and, as a consequence, to improve the overall system throughput performance. However, the performance of the pre-coded multi-beam high-throughput satellite systems is profoundly affected by the scheduling decisions. In particular, the achievable throughput decreases whenever the user channel vectors within the adjacent beams are collinear. However, the optimal performance can be achieved when proper user scheduling selects users with orthogonal channel vectors to be served simultaneously. So we looked up at the literature review and other previous works. So majorly, we had two different paths. The first path was the joint user scheduling and pre-coding problem. However, this problem was non-convex and NP-hard. Hence, obtaining the optimal solution requires an exhaustive search-based user grouping and scheduling, which quickly becomes impractical due to exponential complexity. And the second path, which was much widely used to do perform scheduling, was based on channel orthogonality. So the channel orthogonality was defined either using cosine similarity or geographical user clustering. 2. System model. We consider Unicast multi-beam satellite system. That means we perform unicast scheduling. Hence, the DVB-S2X defined frame includes data that belongs to one user. We also do full frequency reuse combined with the use of spatial interference mitigation techniques such as precoding. The precoding computation and implementation takes place in a single gateway. We also assume that at the gateway we have a perfect CSI knowledge. The multi-beam satellite channel. A single feed per beam payload antenna architecture is assumed where the number of transmitting antennas is equal to the number of beams, which we denoted by K. So y of k in this equation is the received signal and h of k is a channel vector between the transmitting satellite antennas and the user u of k, whereas the x of k represents the transmitted pre-coded signal vector from k satellite antennas. And n of k is a random noise. Y is rearranged all the user's received signals in the vector form, and H represents the system channel matrix, and N is again the noise. The pre-coded signal X is defined using this equation. S is the information vector S that contains the raw symbols coming from the DVB-S2X modulator, and W is the precoding matrix obtained with MMSE design. The precoding matrix W in the MMSE design is defined using these two equations, where alpha is a predefined regularization factor, neta is the power allocation factor, and P tot is the total available power. Also, the H is defined in this equation, where H is a complex channel matrix. B models the path loss, the satellite antenna radiation pattern, the received antenna gain, and the noise power. In particular, the ith and the jth component of the B is given in this equation. Also, GRM is the receiver antenna gain, GKM is the gains defined by the multi-beam satellite radiation pattern and user locations. And D of MK is the distance between the satellite transmit antenna and the mth user's receiving antenna. And lambda is the wavelength for transmission. We also define the phase using this particular equation, where phi is the diagonal phase matrix. Phi of x is a uniform random variable in the interval 0 to 2 pi, and phi of xy is equal to 0 for all values of x not equal to y. Now let us define the problem statement. All the previous work in the literature have focused on channel orthogonality for user scheduling. However, demand was not considered. So, what are demand based systems? Whereas you can see in the picture on the left, which includes the flight or aeronautical user locations at different timestamps of a day, where you can see that the number of flights and the position of the flights keep changing with different time intervals in a day. That's similarly with the figure on the right, where the ships or a maritime users locations at different timestamps of the day, the ships keep moving in throughout the day. That means that the user demand is not constant and the number of users is not constant throughout the day. Also, from this figure, we can see that the traffic for aeronautical and maritime users is different at different timestamp of the day. That means demand at 1 o'clock at night is very less, whereas the demand at 1 o'clock in the morning is very high. The satellite operators and service providers are compelled to provide any agreed throughput to the broadband users. Such agreed throughput will be defined in a legal contract termed as Service Level Agreement or SLA. Consequently, the satellite operators are obliged to provide every broadband user with the agreed levels of metrics defined in the SLA. This further pushes the need for improved scheduling algorithm which jointly intends to achieve the SLA defined user demand. Hence, to perform user scheduling, it is not just important to consider the channel orthogonality, but it is very important to consider the traffic demand of the users. To solve this problem, we propose a solution called the weighted semi-orthogonal scheduling. While most of the literature focused on scheduling design that maximizes the achievable capacity of the system, very few research has been done in demand-based scheduling. Herein, we propose an iterative suboptimal scheduling method, which on one hand intends to orthogonize as much as possible the user's channels, while on the other hand prioritizes the users demanding higher traffic. In order to take into account the traffic demand dm in the scheduling, we associate a generic user m, a coefficient alpha of m. Such coefficient is simply a normalized version of the demand dm and is expressed in this equation. And alpha varies from 0 to 1. Given the cluster of k beams, the goal is to select k users from the user pool of m users at each scheduling time. The first user, U1, is the one maximizing the metric defined in this equation. After the first user has been scheduled, in order to schedule the remaining k-1 users, the metric W of m in this equation is sequentially calculated for each values of m from 1 to m. At each step, the scheduled user U of k is the one maximizing the metric W of m, which jointly accounts for priority and also the channel orthogonality of the previously scheduled users. The WSOS, that is weighted semi-orthogonal scheduling, is followed by precoding to mitigate the interference of the semi-orthogonal scheduled channels. At some point of time, it is important to update the priority coefficient alpha of m, and specifically to rescale it to account for those users which have low demand and have not yet been scheduled. So in this paper, we propose a priority update based on average offered rate. We consider a total number of 60 users distributed across k is equal to 6 beams as shown in this figure. The simulation parameter is given in the table to the right, where we consider a 13-degree east geosatellite. The first result is the per beam average user rate versus the average demand. The proposed scheme satisfies the requested beam demand for all the beams. The proposed scheme satisfies the requested beam demand for all the beams. On the other hand, the benchmarks achieve an offered rate either completely mismatched from the demand, as in the case of the semi-orthogonal scheduling scheme, or not meeting the demand in all the beams, as in the case of demand-based scheduling. Furthermore, even though the demand-based scheduling attains a rate that follows quite well the average demand, at many instances the demand is not satisfied in the case of beam 3, 4, and 5. This is because the cluster demand is too high to be met without proper precoding tailored user scheduling. The second result is the per user rate versus the demand. The conventional semi-orthogonal scheduling is not matching the user demand, resulting on some users receiving capacity that is not requested and some others where the offered capacity falls short in satisfying the user's demand. The demand-based scheduling scheme provides a quite accurate demand matching, but it faces some issues in satisfying the high demand requests. Finally, the proposed weighted semi-orthogonal scheduling is shown to provide a good trade-off between a demand satisfaction and the offered capacity. The other metrics used the other metrics which are used to show the results are the sum rate and the Jain's fairness index. The sum rate C defined in this equation is the average sum throughput delivered by the multibeam system in a particular window of time, where C of k represents the average beam throughput. The Jain's fairness index The Jain's fairness index is a well-known fairness matrix which in this context measures how the provided rate matches the demand at a user level, specifically defining the satisfaction U of M of a generic user M as the ratio between the offered rate and the demanded rate. From the table, the obtained Jain's indices clearly show that the proposed scheme provides greater fairness in comparison to its benchmarks. Also, the achieved sum rate is higher than the demand-based scheduling scheme. As expected, the semi-orthogonal scheduling has a better sum rate in comparison to the proposed weighted semi-orthogonal scheduling. As expected, the semi-orthogonal scheduling has a better sum rate in comparison to the proposed weighted semi-orthogonal scheduling. Nevertheless, the proposed scheme offers better trade-off in terms of fairness, which is considerably much crucial and demand dependent. Finally, the summary. The growing demand for the broadband applications has driven satellite communication service providers to investigate high throughput satellite solutions. While precoding has been identified as the most promising technique to boost the spectral efficiency, new advanced solutions focus on reconfigurable demand based systems, where throughput delivered aligns with the time and the geographical variations of the traffic demand. For such goal, conventional user scheduling algorithms fail to meet the uneven user traffic demand. So, in this paper, we propose a novel Unicast scheduling algorithm that takes into account both the channel orthogonality required for precoding along with the particular user demands. We named such technique as weighted semi-orthogonal scheduling methodology. Supporting numerical results are provided that validate the effectiveness of the proposed scheduling and quantify the benefits over conventional scheduling techniques. Thank you for your attention.